Every time you open Insta, send a message, or load a YouTube video, there is an invisible system working behind the scenes that makes all of it possible. Most people use it every day. Almost nobody understands how it works. I am going to change that for you, starting right now in this 15 minutes. Welcome to CipherNest. And this is the episode 1 of What is a Computer Network? In this video, we are covering 6 things: the definition, the history, the types of networks, and how data actually travels, how devices talk to each other, and the key term every security engineer or network engineer knows cold. By the end of this video, we will have a foundation that most cybersecurity or CS graduates wish someone had explained them this clearly. Let's get into it. So, what actually is a computer network? There is the formal definition. A computer network is a system of two or more devices connected through wired or wireless links, communicating via agreed upon rules to share data and resources. But let me make that real for you. Right now, your phone, your laptop, your router, your ISP servers, they're all part of a network. The moment two devices can talk to each other, then you have a network. And every single network in existence, no matter how simple or complex, is built just upon three things. Number one, node. These are the devices: a laptop, your phone, a server, a printer, an IoT sensor. Anything connected to the network is a node. Number two, links. These are the connections. Could be an Ethernet cable, could be a Wi Fi, could be a fiber optic. The link is what carries the signal between nodes. Number three, protocols. This is one of the most people skip, and it is the most important. A protocol is simply a set of rules that both devices agree to follow so they can understand each other. For example, TCP/IP, HTTP, DNS. These are all protocols. Think of it like a language. If I speak English and you speak Japanese, we can't communicate. Protocols are common language of network. Now, before we go deeper, let me give you 60 seconds of history, because the why behind how networks are built changes how you think about them. In 1960s, the Cold War is at peak. The US Department of Defense has a nightmare. What if the Soviet Union's nuke a single communication hub that takes down all the military communications? Their solution? Built a network with no single point of failure. If one path is destroyed, the data finds another route automatically. The project was called ARPANET. And the idea, packets finding their own path, is still how the internet works today. Fast forward to 1970s. Vint Cerf and Bob Kahan created TCP/IP. This is the universal protocol that lets different networks talk to each other. The network of networks becomes possible. In 1980s, DNS is invented. Now, instead of memorizing IP addresses like 142.250.80.46, you just type google.com. Then the internet becomes human friendly. In 1990s, Tim Berners-Lee builds HTTP and HTML on top of the internet. This is the crucial. The web is not the internet. The internet is the infrastructure. The web is one application running on it. And today, 5G cloud computing, IoT, edge computing, billions of devices all connected using the same foundation ideas from 1969. That's 60 years of the same core architecture. That's how solid these fundamentals are. Okay, network exists at different scales, and there is a simple spectrum you need to know. At the smallest end, PAN, Personal Area Network. It's about 10 meters, like your Bluetooth earbuds talking to your phone, and now that's a PAN. And next, the LAN, Local Area Network. Your home Wi Fi or your office network covers a building, maybe a few hundred meters. Bigger than that, MAN, Metropolitan Area Network. Think a university campus or a city's cable. Covers maybe like 500 kilometers. Even bigger than that, WAN, Wide Area Network. A bank connecting its branches across multiple cities. or a company's global VPN spans countries. And at the top, the internet, which is literally a global WAN, a network of networks connected by undersea fiber cables and a routing protocol called PGP. The size changes, the scale changes, but the fundamentals, nodes, links, protocols, they are the same at every level. Now, here is the part that most people find mind blowing when they first get it. How does your data actually travel across a network? The answer is packet switching. And to understand it, let me contrast it with the old way. The old way was circuit switching. This is how your grandfather's telephone worked. When you made a call, the network carved out a dedicated physical path between you and the other person, and the path was logged for the entire call duration. Nobody else could use it. If any part of the path broke, your call dropped. But the internet does it completely differently. When you send a message, oh, okay, let's say you send a photo. Your device doesn't send it, it has one continuous stream. It breaks it into small pieces called packets. Each packet has a header containing the source address, the destination address, and its sequence number. Then, and this is the key part, each packet finds its own path through the network. Packet 1 might go through London, packet 2 might go through Singapore, packet 3 might go straightly or directly. They arrive at the destination, possibly out of order, and your device reassembles them in the correct way or in a correct sequence. Why does this matter? Two reasons. One, efficiency. The network can use every available path simultaneously rather than locking one path per connection. Two, resilience. Remember why ARPANET was built. If one path is destroyed, packets reroute automatically. There is no single point of failure. This is why internet survives cable cuts, server fails, natural disasters, because packets just find another way. Now let's talk about how devices are organized in a network. What is called network architecture. There are two models. Client server model. This is what you use every day. There is a powerful central server, always on, always available, and the client connect to it to request data. When you open Netflix, your device is the client. Netflix server has the content. You request it and they send it. The downside, the server is a single point of failure. If Netflix server go down, nobody watches Netflix. The second model, peer-to-peer or P2P. Here, every device is both a client and a server. There is actually no central controller. Every peer shares what it has directly with other peers. You have probably used this without knowing. BitTorrent is P2P. Blockchain is a P2P. Some video calling apps use P2P for direct connections. And the upside is, it is incredibly resilient. There is no single server to take down. The more peers join, the stronger the network gets. The upside down, it's really very hard to manage, harder to secure, and harder to enforce rules. Most of the internet is client server. Before data can travel, it needs a medium to travel through. Let's cover the four types quickly. Twisted pair copper wire. This is the internet cable plugged into your router. Two wires twisted together to cancel out electromagnetic interference. Handles up to 1 gigabyte per second and its range is about 100 meters. Coaxial cable. The thick cable your ISP runs to your home. Copper core with a metallic shield used for cable internet delivery. Gets up to 10 GB per second. Fiber optic. This is where it gets incredible. Instead of electrical signals through copper, fiber sends light through glass. Zero electromagnetic interference, terabytes per second, hundreds of kilometers without signal loss. The entire backbone of the internet, including the cables running under the sea between continents, is fiber. And finally, Wireless radio waves, 5G, 4G, Wi-Fi, Bluetooth, satellite. The advantage is obvious. No cables. The limitation. You're sharing the airspace with every other wireless device around you. Your data moves through some combination of all four of these every time you do anything online. Now let's talk about how to measure a network. These six matrices are the ones every network engineer knows, and the one you will see in every interview. Think of a network like an highway. Bandwidth is the width of the highway. How many lanes it has, how it is measured. It is measured in Mbps or Gbps, and it's the maximum capacity, not what you actually get. Throughput. Throughput is how many cars are actually moving. Always less than or equal to bandwidth. Reduced by congestion, packet loss, overhead. Latency is how long it takes one car to drive from start to finish. Measured in milliseconds. Jitter. Jitter is the variation in latency. If your latency is a stable 50 ms, then it's fine. If it swings from 100 to 200 ms, packet to packet, your voice call will sound like a broken radio. And no, that's a jitter. Packet loss. Packet that never arrive. Above 1% you will notice it. TCP will retransmit the lost packets. UDP don't, which is why video calls sometimes glitch instead of pausing. And hop count. The number of routers your packet passes through. Each hop adds a tiny bit of latency. Run traceroute in your terminal and you literally see every router your packet touches on the way to destination. Before we wrap up, let's cement 10 terms you will see everywhere. IP address, the logical address of a device, like a postal address for data. Use it to route packets to the right destination. Port identifies a specific service on a device. HTTP runs on port number 80. HTTPS runs on the port number 443. SSH on 22. Same device, different services, different ports. MAC address. MAC stands for Media Access Control. The hardware address burned into your network card at the factory. Use it for delivery within a local network. Router. The device that forwards packets between different networks based on IP addresses, and that's the post office. Switch connects devices within a single network using MAC address. Smarter than a hub, it sends data only to intended device, not everyone. Packet. The unit of data. Header plus payload. Protocol. The agreed upon rules. Both sides must speak the same one. Firewall. Monitors traffic and blocks or allows. It is based on security rules and it's your network security guard. Node. What is a node? Any device on a network. DNS. DNS stands for Domain Name Server. Translates google.com into an IP address. The internet's phone book. Without DNS, you would have to memorize IP addresses of every website. Alright, let's recap what you have learned. Every network needs nodes, links, and protocols. Network scales from your Bluetooth earbuds all the way to the global internet. The data travels as packets independently, resiliently, find their own path. The internet can be recognized as client server or P2P. The signals travel through copper, coax, fiber, or wireless. And now you know the 6 matrices that define network performance. And that is episode number 1. And that is the foundation. In the episode 2, we are going into network topologies. Bus, star, ring, mesh, hybrid. When each one makes sense and when each one fails. If this helped you, make sure you subscribe and leave a comment. And I will see you in episode 2.